So for other perturbations, for example, you can perturb the rather than location, the height of the tent map. In this case, we can no longer had the proofs of what kind of quasi-physical solution this leads to, but we can compare the density of the physical solution, right? We can numerically show the difference between the density of the physical solution with the density of the shadowing solution. They again dramatically different, right? Physical solution, shadowing solution. Okay. Yet another type of perturbation, instead of moving the location, we actually make the map nonlinear. Again, physical solution would have a density that's actually sloped down, right? Something like this. And the shadowing solution, well, completely different. And it turns out like this kind of a fractal features of the density seems to be a hallmark of this kind of a quasi-physical solutions. Right, anything you see the quasi-physical solutions, you get kind of a fractal pattern in the density. Now the Lorenz equation. So for the Lorenz equation, because we want to show the densities, we actually look at the Lorenz map as opposed to the Lorenz equation. Okay, so for the Lorenz map, I mean, if you're familiar with the Lorenz system, you know there are three important parameters: sigma, rho, and beta. They all have some aspect. They all have things to do with the circulation of atmosphere. They change, for example, the Rayleigh number and the aspect ratio of the convection box. So this is the perturbation in the Lorenz map. If you change sigma from 10 to 15. Away from the standard set of parameters. The density of the physical solution, if you make that perturbation, is like that. You get a smooth, nice distribution. However, the density of the shadowing solution, you can see the same kind of fractal patterns growing hairs on top of the distribution if you compute the shadowing solution and look at its density. If you perturb rho, the Rayleigh number from 28 to 30, right? This is the kind of perturbation resulting from the perturbation in parameter. The map goes from the blue to the orange curve. Density of the physical solution is like that. Density of the shadowing solution has hairs growing on top of it. If you perturb beta, the aspect ratio, the density of the physical solution looks nice and smooth. Density of the shadowing solution has hairs growing on top of it. So here, I can pretty confidently claim that when you do shadowing, you are very likely to get, instead of physical solutions, quasi-physical solutions. Therefore, the argument based on shadowing doesn't really work, although you have a solution that has statistics close to the controlled system. But that solution is not representative of the solution of the uncontrolled system. So you cannot use the closeness of statistics of these two solutions to argue the closeness of the statistics of the perturbed and unperturbed systems, because one of the trajectories is actually non-physical, right? Or can be non-physical.